Okay, well, hopefully this is working. Just hit the go live button. This is the first time that I've done a live stream, so hopefully things are working. And just thought a nice way to start would be to introduce you to me and my wife's dog, Curie. She's very cute and a wonderful prop to ingratiate myself with my audience. Really quick, aren't you just the cutest little prop? Okay, I am going to put her to the side. Again, hopefully this is going through. I'm hoping if someone sends a quick chat message just to make sure that both the audio and video are working decently well. There is a little bit of a delay on here. But yeah, I'm going to put her in the other room just real quick, and then we'll get started. Okay, so yeah, looking forward to. I've been looking forward to this live stream, and especially looking forward to talking about this news from the NANOGrav collaboration. You may have seen in the news yesterday that there was a detection of gravitational waves from this collaboration called NANOGrav. And the NANOGrav collaboration, the way that we're going to talk a little bit about the way that they have detected this gravitational wave, these gravitational waves, more details about how this was actually done, some of the background information for gravitational waves, why this is exciting to astronomers, and basically just have lots of time for hopefully questions. So if there's people that are viewing that have questions, you can throw those questions in the chat. As always, please try to be courteous and respectful when both asking questions and providing comments. So yeah, let's just jump into things. So again, I'm hoping that this is hoping that the tech stuff is working. Yeah, hopefully the tech stuff is working, but we'll just, see how things are going. So, the NANOGrav collaboration uses pulsars, which are a type of dead star, to try to detect ripples in the curvature of space-time. Now, there's a lot going on there in that sentence to kind of break down, so I'm just wondering whether this is actually going through. I'm going to just hold on for 1 second just to make sure that the stream is actually working. Okay. Well, hopefully anyone who's interested is actually able to access this. So let's jump right in. So as I was saying, my apologies for the tech issues and if there's any delays in here. So as I was saying, the NANOGrav collaboration is trying to use pulsars to detect these ripples in the curvature of space-time. And we use radio telescopes to monitor the properties of these pulsars, and the idea is these pulsar signals would be affected by gravitational waves. And if I were to look at a single pulsar and look at the signals that I'm receiving from that pulsar, it would be basically impossible to identify whether the signal from a single pulsar is actually caused by a gravitational wave, or whether we would, or whether that signal is coming to us from some other object. So let's talk a little bit about this. I'm gonna make sure I can switch to a slightly different view. Let's talk about what these pulsars are first. They are basically a type of dead star core. So a type of dead star core. And during, when a high mass star reaches the end of its life, it's fused in its core hydrogen to helium, and then for massive stars, they can fuse helium into carbon, carbon into oxygen, oxygen into neon, into heavier and heavier elements until it gets to iron, and you can't get energy out of fusing iron. So this star core, so let's say we've got the core of this star. Gravity is constantly trying to crush the star. But there's a fusion reaction going on inside of the core that supports it against collapse. But once all of the kind of nuclear fuel is used up in the core, those forces fail, those pressure forces fail, and that core collapses into what we call a neutron star. So let me kind of share a couple of fun facts about these neutron stars. Okay? So these cores that have collapsed down into these very small objects, they're more massive than the sun. You only get these from high mass stars. They're more massive than the sun, but around the size of the island of Manhattan. These are extremely crazy objects. They are some of the most extreme cases of physics that we actually see. So these materials are so dense. I want to talk just a little bit about how crazy these objects are. 1 teaspoon of neutron star material would have around the mass of Mount Everest. It is basically as compact as material can get. And when these things collapse, when these things collapse down, they have a little bit of rotation to begin with, so as they collapse down, their spin rate is going to increase. Just like a figure skater spinning around and then pulling their arms in rapidly, if you pull your arms in rapidly as you're spinning, you'll feel your spin rate go up. So this thing is going to be spinning very fast. So we get this high spin. And all of the magnetic fields that this star had before it went through this collapse also get concentrated. So it's got these very, very strong magnetic fields. So this is these loops are representing the magnetic fields that are coming off of this. And that combination of these very strong magnetic fields that are spinning in this particular way will produce this burst of radiation kind of flying off of either pole of that neutron star. So this thing is going to be spinning around, and every spin, if we're in the right location, if the Earth is at the right location and we're looking at this with a radio telescope, then as this thing is spinning around, it's basically going to act like a lighthouse in space. Every time this thing spins, we're going to get a little burst of radio waves sent towards us. There is also other kinds of radiation that are produced by this, but radio waves is some of the strongest type of radiation that is produced by these particular kinds of systems. And radio telescopes, we can use those to accurately measure these pulses. This is why we call them pulsars. So every time this thing spins on its axis, we're going to see one of these little bursts of radio waves. Okay? We can actually take this radio signal and send it through a speaker to actually hear these pulses. So for example, hopefully I have the volume settings right so this isn't too loud or quiet for anyone. But this is the signal from one of these spinning pulsars. So basically, as this pulsar spins and is sending out this beam of radio waves, those clicks that you're hearing are, every time this thing spins, it sends a little burst of radiation our way. That one, that particular pulsar, is actually fairly slow. This is another example of a pulsar. This is the crab pulsar. Again, if you're wearing headphones, you might want to turn down the headphones a little bit because I don't know how loud this is going to go through on the stream. But this is the crab pulsar, and it spins 33 times per second. So that sound that you're hearing is, again, the radio signal from this thing spinning very, very rapidly, and every time it points towards the Earth, it sends out this burst of radio waves, and we can detect that burst of radio waves using telescopes like the Green Bank telescope. This is the Green Bank telescope from that's in West Virginia. Let me zoom in on this a little bit more so you can see it a bit better. And again, these telescopes on their own are just amazing pieces of technology. This is the largest fully steerable radio telescope in the world, and it's one of the it's one of the key instruments that NANOGrav uses to detect and measure these pulsars. But even that crab pulsar that was spinning 33 times per or around 30 times per second, that's also considered a fairly slow pulsar. There's another class of pulsars, and these are the ones that NANOGrav is interested in. Pulsars that have actually stolen, accreted more material from a nearby neighbor or some near gas clouds, something that causes it to spin up even more, and these ones can spin hundreds of times per second. So this is the pulsar JO437, and this is the signal that we get from that particular pulsar. Okay. So again, I'm hoping that wasn't too loud. My apologies if that was. I'm hoping I didn't, burst anyone's eardrums by doing that. That pulsar is spinning so fast that you can't actually hear the individual pulses with your ear. It just sounds like a constant pulse. Again, this neutron star, this is an object that is more massive than the sun, crunched down to the size of the island of Manhattan, and spinning faster than a blender. These pulsars are crazy objects, super interesting objects in their own right. And these pulses, when we receive these pulses, so let's say we are, we've got the Earth over here. These pulses are being sent towards the Earth, and we can receive them with extremely, extremely high accuracy. So there was a question, is it only gravity holding it together? It is some of the most extreme versions of gravity holding this thing together. Again, if you had this neutron star material, this exceedingly, exceedingly dense material on the Earth, if you had a teaspoon of that material is so compact that without that really strong gravitational field around the neutron star, that material would just violently explode like many, many nuclear bombs. So yeah, it is the thing that's holding this thing together is that intense gravitational pull of all of that material that was in the star's core has collapsed down, and when masses get closer together, those gravitational forces are going to be increasing more and more as this thing gets crunched down into that really, really small size. Again, we're talking an object more massive than the sun, smaller than the island of Manhattan for these objects. So they are super, super interesting in their own right. What NANOGrav does is study these pulsars and study multiple pulsars across the sky, because these pulses can arrive very, very regularly. So very regular arrival times. Extremely regular arrival times, which means if a gravitational wave is passing by, gravitational waves, I should kind of talk about those a little bit. So we've got these pulsars, they send out this repeating signal, and those signals arrive with great regularity. Regularity rivaling that of atomic clocks. There are actually some proposals that on long time scales, these pulsars would be a better measurement device, a better way of characterizing time than atomic clocks, at least over long time periods. But gravitational waves, let's talk about that piece for a minute. according to Einstein's theory of relativity, massive objects can distort space and time around them. So I've got just a bunch of materials set to the side here, and I'll try to bring them out as they're useful. And the common analogy for gravity, for Einstein's theory of general relativity, is that massive objects will distort the geometry of space and time around them. And that distorted geometry of space and time will affect how objects move. The analogy for this is the rubber sheet analogy. It's done a lot. I think it's overdone a little bit, but it's a pretty good analogy of how general relativity works. The idea is, imagine you have a big rubber sheet and you put a mass in the middle, and that mass sinks down a little bit and distorts the shape of that rubber sheet. So if then you took a little marble and rolled it beside that heavy object, the curvature of that rubber sheet is going to deflect the path of the marble. In a very, very similar way, again, the idea is that matter and energy will change the geometry of space and time, and that changed geometry of space and time will affect how objects move. And there are a lot of different phenomenon that have been studied that match up with Einstein's theory of general relativity. I'm kind of throwing a lot here right away. So there's precession of planets, gravitational redshift. Right now I'm making just a whole bunch of claims about this. So if anyone in the chat wants to have a deeper discussion on any of these topics, then we can go into more detail on that. Again, I encourage lots of questions. It makes the presentation more interesting when there's lots of questions coming up, so feel free to throw those into the chat when they come up. But there's lots of different kinds of tests that we can do looking specifically at the predictions of general relativity. And so far, general relativity has been matching all of these predictions. Okay. Let me jump ahead. So the idea is, when we talk about gravity as this curvature of space-time, if I have particular setups of objects, so let's say I have two masses that are orbiting around each other. Those masses, say two black holes that are orbiting around each other. When those objects orbit around each other, they can actually produce ripples in the curvature of space-time. So those gravitational waves can affect how, what the geometry of space and time is like. And that effect will propagate away from its source. And that affects how we measure distances and how we measure time. So these gravitational waves will affect the geometry of space and time. So let's put these two ideas together. And with these gravitational waves, if I can measure the properties of these gravitational waves, I can basically use this as a new kind of telescope. Most of what we know about astronomy comes from studying the properties of light. For hundreds of years, it was only visible light that we had access to. Well, basically for most of human existence, even when we were just, looking up at the sky and without any telescopes trying to find patterns, we were basically just using visible light to study astronomy. More recently, we've been able to do things like radio astronomy, look at the radio part of the spectrum, look at the infrared part of the spectrum, ultraviolet, X-rays, and gamma rays, look at different parts of the electromagnetic spectrum to get more data and better understand what sort of systems are out there. Because different kinds of physical systems will produce different kinds of light. What this NANOGrav collaboration is trying to do, along with other collaborations trying to detect gravitational waves, for example, the LIGO detector first detected gravitational waves that was 2015 when they made their first direct detection of gravitational waves. But we want to look at all sorts of different kinds of gravitational waves. And if we can measure these gravitational waves, we can basically use this as a new kind of telescope. One that doesn't look at the light coming to us from distant objects, but one that actually looks at these gravitational waves. Imagine there was a swimming pool, and someone in the far end of the pool is swimming around and splashing around. But let's say you couldn't see that far end of the pool. If you can detect the waves in the water that are coming off of them, you would be able to figure out what you could figure out where they are, how much they're splashing around, are they moving in different ways? There's a lot of information that you could extract from that. So again, another question in the chat, what can you see with gravitational waves? Well, it depends on what kind of systems will actually produce these gravitational waves. Let's see if I have something on here that... So the kinds of systems that would produce these gravitational waves, the clearest one is if I have two objects orbiting around each other. So if I have two, let's say, in this case, we're going to be looking at black holes. If I have two black holes spinning around each other, those are going to produce gravitational waves. And remember that black holes on their own don't emit any light. If there's stuff falling into the black hole, we might be able to see the stuff around the black hole, but the black holes themselves don't give off any light. So we might be able to see these kinds of systems if we're looking at them using these gravitational waves. Other things that would be giving off gravitational waves are, other types of compact objects moving around each other, like if you have two neutron stars moving around each other, we've detected gravitational waves from there. The LIGO collaboration has detected those gravitational waves. Other objects, things like neutron stars, if a neutron star has a little mountain on it, so it's a little bit asymmetrical, as that thing spins, it will also produce high-frequency gravitational waves. Things like supernovas would give off gravitational waves. And it's possible that in the very early universe, there would be events in the very, very early universe that would have produced these gravitational waves. And one of the things that the NANOGrav collaboration is trying to do is seeing if they can detect any of those exotic sources. So maybe there's some sources that we just don't know yet, and we want to look at the sky and gravitational waves to see if we can detect these sorts of things. So one of the big questions is, how do we actually do this? How do we actually try to detect these gravitational waves? Well, we need the gravitational wave to affect something that we can detect, some detector that we've built or something that's happening in nature. And for the NANOGrav collaboration, what we're trying to do, let me jump forward just a little bit. For the NANOGrav collaboration, we've got these pulsar signals that, again, are very, very regular. We can predict down to, for some of our best pulsars, down to a few tens of nanoseconds when a pulse is going to arrive years from now. So years ahead of time, we can say one particular pulse is going to reach us at exactly this time. And we can be accurate to, some tens to maybe 100 nanoseconds of accuracy, which is phenomenal accuracy. But gravitational waves, well, those gravitational waves affect space and time. So if a gravitational wave is passing by and we have all these pulsar signals coming towards us, that gravitational wave can distort space and time to slightly delay or slightly advance when these signals actually arrive at the Earth. The problem is, even for really strong gravitational wave signals, this would be a super, super minute effect. Again, on the order of some tens of nanoseconds. And another problem is that, let's say I'm just looking at one individual pulsar, and I have a model for when these pulses should arrive, You know, I've observed this, I've done the timing for this, I model this particular pulsar and I say, I'm pretty sure I know its properties when, and I can make some predictions on when these signals should arrive. But in any sort of measurement, there is always going to be some measurement error. So maybe I'm looking at this one pulsar and I see one pulse arrive a little bit early, another pulse arrive a little bit later. There's still going to be some noise in there. What we have to try to do is distinguish what is a gravitational wave, what part of that signal is a gravitational wave, and what's coming from some other source of noise. And there are a lot of sources of noise that would be much stronger than the gravitational wave signal. Okay? Sometimes by many orders of magnitude. So the goal is, first, we have to try to get rid of as many of those noise sources, get rid of or account for as many of those noise sources as possible. But even then, for a single pulsar, I might still say my ability to get rid of those sources of noise might be incomplete. So if I have a single pulsar, I'm still not going to be able to make a reliable measurement, which means I have to look at an entire set of pulsars. And this is what NANOGrav and other pulsar timing arrays have been trying to do for the last 15 years. Look at many pulsars spread across the sky, timing each of those pulsars, trying to build these models of when these pulses should arrive, and then looking for patterns in these pulsar signals that are specifically attributable to gravitational waves. So we're trying to look for these timing differences. So look for timing differences. Differences between those pulsars, or in a single pulsar measurement, and then get rid of all sources of noise, or get rid of as much noise as possible. Again, there's no such thing as getting rid of all noise. All measurements are going to have some amount of noise with them, and we just kind of have to deal with that. That's the nature of data. But we want to get rid of as much noise as possible, and then we want to look for patterns that are specifically attributable to gravitational waves. So look for patterns. Attributable, specifically attributable. Specifically attributable to gravitational waves. Okay. But let's see how this would work. So let's say I've got the Earth here, and I've got a bunch of different pulsars that are sending out these signals. So a pulsar over here sending out some signals, maybe one further away sending out some signals. They're all going to have, some of their own individual properties. So again, we're looking at all these pulsars spread across the sky. Gravitational waves should cause a very specific pattern in how these pulsar timing differences appear across the sky. And the reason for that is, if we go back up here, if a gravitational wave passes by, it distorts space and time in kind of a stretching and squishing way. So if I have a gravitational wave coming towards me, it will actually take the geometry of space and time and alternately stretch and squish it in different directions. And that has some very, very helpful effects for measurement. Because if I have this stretching and squishing signal coming towards me, let's say I've got a gravitational wave that's passing by, and it's squishing space in this kind of a way. So let's say it squishes space like this, slightly. Okay. Well, signals from pulsars over here and over here, those pulses should arrive a little bit early based on how it's squishing that space. Signals from pulsars up here and down here, well, they should be a little bit later. They should be coming a little bit later based on how space has stretched in that direction. Pulsars kind of on the... So these ones would arrive early. This would arrive early. And these would arrive late. And pulsars kind of on the diagonal here, these would not really see much of an effect. So no change. So no change there, no change there, no change there, no change there. Okay. And this particular pattern of which pulsars on which parts of the sky are arriving early, which ones are arriving late, well, that is characteristic of the signal for a gravitational wave. We can't think of any other thing that would affect our signals in this particular way other than gravitational waves. For example, let's say what if there was a different pattern? Let's say all of my signals were arriving early, or all of those pulsar signals were arriving late. Well, that could be due to a problem of how I'm timing it on the Earth. Maybe my atomic clock on the Earth is a little bit off, so I'm mistakenly thinking all of these signals are arriving early or all of these signals are arriving late. That would be a correlated pattern between those measurements. All of them would arrive early or all of them would arrive late if it's a problem with my atomic clock. Let's say I have one where the pulsars on this side are all arriving early, and the ones on this side are all arriving late. Okay? Notice that's not the same pattern that we've talked about up here. If all the pulsars on one side are arriving early and all the pulsars on the other side are arriving late, well, maybe I'm not accounting for the motion of the Earth through space, so I'm a little bit further ahead. The Earth has moved a little bit this way, which is making it look like these are arriving early and making it look like these are arriving late. So that would be a different kind of pattern from a different source of error. But for gravitational waves make this kind of a pattern. On the two sides, it would be early, top and bottom, they would be late, and forward and backwards, not as much of an effect if you're directly in front of that gravitational wave or directly on the other side of that gravitational wave. So it's this pattern that the NANOGrav collaboration was looking for. And if you take this particular pattern and say, let's suppose there's gravitational waves coming from every which way. Let's say there's these gravitational waves coming from every single different direction. We can still look for specific kinds of correlated patterns. The specific kind of pattern is something called the Hellings and Downs curve. The Hellings and Downs curve. It looks something like this. So what are we talking about for this part? What this is measuring is how much correlation do I get? How much matching up do I get in my pulsar signals? Are they all arriving early? Are they all arriving late? Or are, certain pulsars on different parts of the sky, this one's early, but this one's late? So how matched up are they? How correlated are those signals? Versus how far apart in the sky are my two pulsars? If I just pick two pulsars at random and say on the sky, there's a certain angle between them. So if I was looking at, on my diagram over here, let's say I was looking at this pulsar and this pulsar. What's the angle between those? Or let's say I was looking at this pulsar and this pulsar. What's the angle between those? Well, what this graph is showing is if the angle between them is really small, there should be quite a bit of correlation between those signals. They're either both arriving early or they're both arriving late. If they're at around 90 degrees apart on the sky, those should be anti-correlated. So when one's a little early, one would be a little bit late. The other one would be a little bit late. We get that anti-correlation, that negative correlation. If they're at exact opposite sides of the sky, then once again, we should get a little bit more correlation. If one is late, the other is late. If one is early, the other is early. So this is the prediction for exactly how correlated these pulsars should be. This is specific to gravitational waves. And it's this pattern that the NANOGrav collaboration was trying to look for. But the problem is, again, there's always going to be sources of noise. This would be the ideal pattern if there were no other sources of noise other than, just saying, well, these pulsars are at different locations, at different parts on the sky. If we add noise in, well, there's still that pattern. It's just harder to see. And we need more data in order to be able to distinguish when am I actually seeing this particular pattern. And the less data that you have, the harder it's going to be to find that specific pattern. Like if I run this a couple of times, just with randomized numbers, so I set this up so it can randomly generate these, this pattern can be kind of hard to see unless we have a lot more data. The more data we have, the easier it's going to be to see these particular patterns. So this is the paper, the NANOGrav 15-year data set, evidence for a gravitational wave background. Again, lots of people involved. It's been a while since I was in this collaboration. I was in the collaboration from about 2010 to about 2016 is when I switched over to more of a teaching position instead of doing research. I still recognize a lot of names on here. So yeah, I'm super happy for this team. They're amazing people working here. But getting to the actual measurement, this is that Hellings-Down curve that they were detecting. We're saying how correlated are those pulsar signals given different angular separations. So the dotted line is that Hellings-Downs curve, and the dots are the actual data measurements that they have from looking at lots and lots of these different pulsars. So before this, a few years ago, NANOGrav and some of the other pulsar timing arrays, they had detected some signals that looked like gravitational waves, but this is the first time that we've actually been able to accurately characterize this Hellings-Downs curve, and that specifically showed the signal that they were identifying is very, very likely from gravitational waves. Now, there are still large error bounds on a lot of these, but as time goes on, we're going to keep on getting more and more data, and as we get more data, the sensitivity of this pulsar timing detector is only going to increase. One of the things that I wish they would have highlighted a little bit more in the press conference yesterday is that this detector, how long it's running, the longer it's running, the more accuracy we're going to get. It's not like we're going to have to redo this experiment and get a whole nother 15 years of data to get something similar to this again. As we take more data, that just gets added on to this data, and our abilities for these two. Sorry, I lost my train of thought. Our ability to use these pulsars as a way of detecting these very, very low frequency gravitational waves is directly related to how long this has been running for. I really think that in 100 years, we're still going to be using this data. Because if I want to measure gravitational waves with periods of 100 years, I need 100 years of data. We're 15 years in, and we're going to be continuing to analyze this data. We're going to be continuing to make the data sets better. And the detection rate, our ability to characterize and increase the accuracy of this, is just going to increase with time. So there's a question of why is the 180 degrees less correlated than the 0 degree point. So at 0 degrees, they're pretty strongly correlated. At 180 degrees, it's less correlated. That has to do a little bit more with the details of how the detector actually works and how these gravitational waves will advance or delay the signals. So let me give a quick example. So let's say I've got a gravitational wave that is going in this direction. Okay, so the gravitational wave is going this way. And actually, I'm going to put more of these lines on here. This is going to get slightly technical, but again, just let me know when clarifying questions are being asked, because having questions being asked is always more interesting than me just talking. So let's say we've got the Earth, and let's say we've got some pulsars. So let's say there's a pulsar there and a pulsar there. It can't be directly in line with the gravitational wave, because then the gravitational wave doesn't actually affect the pulse. But let's say they're pretty close to being aligned. So both of these are sending pulsar signals towards the Earth. Okay. So both of those stars are sending pulsar signals towards the Earth. If the pulsar signal is going in the same direction that the gravitational wave is moving in, you can kind of think of it as that pulsar signal is going to kind of ride the gravitational wave. It's going to be quite a bit more advanced or quite a bit more delayed. Whatever's happening to that pulsar signal, it's kind of riding along with one gravitational wave, getting that same effect always in the same direction. So it's always going to be advancing it a little bit more, or constantly delaying it a little bit more. That effect is going to be magnified for this pulsar. Okay? If there was another pulsar beside it, well, that one's also going to get the same effect as these two pulsars are going to get that same effect of kind of riding that gravitational wave. Okay? So they're going to be affected in the same kind of way. The one on the other side, well, that's acting against the gravitational wave. So when a gravitational wave crest comes by, it might advance that signal, but then a valley is going to come by, it slows it down a little bit, so it kind of cancels out more of the signal. So that's why they're still going to be correlated in general a little bit in the same direction, but not nearly as much as if they're on the same part of the sky. Okay. And again, the picture that I'm giving right now is still an oversimplification of all of the mechanics that are going on in here. But this is kind of a good aside of when you're doing any kind of measurement, even just using like a ruler, you always want to have a decent understanding of how does your measurement device actually work. So for example, for rulers that have like 0 right at the end, it's never a good idea to use that as your 0 point, because having that right at the end, well, it might be a few fractions of a millimeter off a little bit in either direction, so it's better to start somewhere in the middle so you have a good kind of reference point there. Understanding your measurement devices, that works for rulers or stopwatches, identifying that, well, there's a certain reaction time that we have for that. That works all the way up to these, literally galaxy-sized detectors using these pulsars. So again, but even though we have these large error bounds, it still seems that we're getting some pretty good evidence of this Hellings and Downs curve, and again, that is specifically associated with gravitational waves. We do not know of any other source that would cause this kind of correlation. Again, if it was a problem with say, atomic clocks on the Earth, and maybe our atomic clocks are off, that correlation should be 1 across the board. They should all be early, no matter what direction from the sky they're coming from. If it was a problem with how the Earth is moving through the solar system, well then, ones in front, this correlation would probably be more like 0, would probably look a little bit more like this. Again, you'd have to go through the calculations to see it exactly, but that correlation would probably look a little bit more just like that, would be my guess, if it was just the motion of the Earth. This particular curve, this is characteristic of gravitational waves. One of the other things that this paper is reporting on and focusing on is, what is the spectrum of these gravitational waves? Okay. So we can look at a graph of how strong are the gravitational waves. So this would be strength versus frequency. There are different frequency gravitational waves. So for a quick example, let me let's do this. So let's say I'm looking in the range of tens to hundreds of hertz, or tens to thousands of hertz. This would be the region that LIGO is effective at measuring. The Laser Interferometer Gravitational Wave Observatory, you may have heard of this detector. They were the ones to make the first direct detection of gravitational waves in 2015. Okay? They actually got the Nobel Prize for that discovery. Very well earned. But those aren't the only gravitational waves that are present. The range that NANOGrav is looking at is around the, tens of nanohertz to, I think, around 100 nanohertz. I should probably double check those numbers on this, but in the kind of nanohertz range. So that is very, very low frequency. These are periods on the order of years. Periods around a year or so. So this is where pulsar timing is sensitive to. Which means if I want to measure something that has a period of a few years, I need at least that few years of data to be able to detect anything in that case. If I want to find something with periods in the order of tens of years, well, I'm going to need tens of years of data, which is why I was saying that this pulsar timing project, it was never going to be we got all the information that we need in one fell swoop. It was a very quick discovery. This was always going to be we're gradually building our understanding. The news that was announced yesterday was a really good milestone, but again, it is just a milestone on the way to making more and more discoveries. And as we gather more data, the NANOGrav collaboration and others like it are already analyzing new data that's been coming in. They're constantly taking new data, and as that happens, our baseline for just how much data we have to work with and over what time frames, that's just going to be getting better and better, and allowing us to measure lower and lower frequency gravitational waves. And one of the reasons that is interesting is these gravitational waves, the kinds that we're looking at here, those gravitational waves should be coming from supermassive black hole binaries. So supermassive black hole binaries. These are the most likely source. They're not the only possible source, but they are the most likely source of these very low frequency gravitational waves. We know that in the centers of most large galaxies, there are supermassive black holes. For example, in our own Milky Way galaxy, there is a supermassive black hole that is around 4 million times the mass of our sun. In other galaxies, we see supermassive black holes that can be billions of times the mass of our sun. So most galaxies have these supermassive black holes in them, and we know that galaxies merge. So if I have two galaxies, both having a supermassive black hole in them, and they merge together, those supermassive black holes might fall towards the center and start orbiting each other and giving off these very, very low frequency gravitational waves. And that's one of the sources that we're specifically trying to look for, trying to identify, can we detect the properties of these supermassive black hole binaries? Because if we can start to measure their properties, first, we might be able to verify that, yes, these supermassive black hole binaries actually exist. There's some observational evidence for it. It's not super, super strong. But a gravitational wave, a direct resolvable gravitational wave detection would be super, super exciting to see. And if we can measure this kind of hum from the universe of all these supermassive black hole binaries that are all giving off gravitational waves in all sorts of different directions, if we can measure the properties of that overall hum of the universe, we can start narrowing down, well, how often do these supermassive black holes merge? This tells us something about the merger history, the galaxy merger history of our universe, which, again, along with studies being done by the James Webb Space Telescope that's also trying to understand, early universe physics, how did galaxies evolve, we're going to be able to get a better understanding of how galaxies formed, what the early universe would have looked like, what its properties are. This is one of the things that these NANOGrav observations in the future might be able to do a better job of distinguishing between. And one of the most exciting potential sources, again, there's strong debate on whether pulsar timing would be able to actually measure this or not, would be a gravitational wave background from the early universe. There could be things called primordial gravitational waves that would have been produced in the first fraction of a second after the Big Bang. And then as the universe expands, just like light gets redshifted, those gravitational waves would also be redshifted into very, very long wavelengths. Pulsar timing might be able to measure those. There's other methods that use the something called the cosmic microwave background, trying to see if these gravitational wave signals might have been imprinted on there. So these observations could potentially give us some data, give us more data that we would not be able to get any other way about what the properties of the very earliest moments of the universe might have looked like. There are other exotic sources of gravitational waves, potentially things like cosmic strings or, stuff, again, primordial gravitational waves left over from inflation. But this gives us a brand new way of doing astronomy. So again, these observations from the NANOGrav collaboration, they're super exciting to me. Again, not only just partly because I had the opportunity and the pleasure to work with this collaboration, again, quite a while ago. So super happy that they were able to report on these exciting results, and still just recognizing that this is just the first step in being able to measure more different regions of the gravitational wave spectrum. And just like we want to measure light in all different parts of the spectrum. We want to be able to measure these gravitational waves in all sorts of different parts of the spectrum as well, because each part of that gravitational wave spectrum tells us different things about the universe, and we can use it as a different kind of tool for studying the universe. Okay, so those are some of the main things that I wanted to talk about, but I'm happy to answer questions. I know there's not a huge number of people on here, but if there's questions that people want to chat about, then I'm happy to do that for a little bit. The future of gravitational wave research. So again, we've got a bunch of different kinds of observatories looking at different parts of the different parts of that gravitational wave spectrum. So, for example, LIGO, they've been actually going through some updates recently to increase their sensitivity, to look at things like additional detectors. So there's some detectors in Japan and I think India that are going to be coming online soon that will allow us to measure these high-frequency gravitational waves better. For pulsar timing, we've already got, at the same time that the NANOGrav collaboration was announcing their results, there were also collaborations in Europe, the European Pulsar Timing Array, Australia, the Parkes Pulsar Timing Array. There's a Pulsar Timing Array in India. There are also radio telescopes in China and some other, I think, the southern part of Africa. Some other telescopes that are coming online and going to be also contributing to better timing, looking at more pulsars to get a better idea of what's of these observations. But we've already got a lot of data, and what's going to be coming up next is the NANOGrav collaboration, the European Pulsar Timing Array, the Parkes Pulsar Timing Array, combining their data together in a structure called the International Pulsar Timing Array, and saying, let's lump all of our data together and see if we can increase the accuracy. Again, these different collaborations were announcing also yesterday, and from what I could tell, they were getting very similar results, which is great to see because they're using different telescopes, they're doing different methods of data analysis, and it's really encouraging to see that everyone was getting the same general results for this one. Also, hopefully, eventually, this window that I haven't included in here, there's been a proposal for a gravitational wave detector in space that would be a set of spacecraft that sends a laser beam between the spacecraft as another way of measuring kind of mid-frequency gravitational waves. This is slated to launch in, I think, 2036. I am kind of hesitant about that because for the last, 20 years, this LISA mission has been, 20 years from being launched. So, again, it's had a lot of delays, so we'll see if it actually gets the funding that it would need for that, but across the entire gravitational wave spectrum, there's a lot of new research going on, and some of the best ones are what's called multi-messenger astronomy, where we can take gravitational wave measurements, measurements from all sorts of different types of telescopes across the entire light spectrum. Also looking at things like cosmic rays and neutrino observations, using all of those detectors together to do what's called multi-messenger astronomy. And that's going to allow us to answer questions that no one method would be able to do on its own. So there's a question, do gravitational waves also get redshifted? According to Einstein's theory of general relativity, gravitational waves should get redshifted just like any other kind of waves, including owing to the expansion of space. So some of those gravitational waves that could have been produced in the very, very early universe, even if those were produced at a very, very high frequency for those gravitational waves, as the universe expands, those wavelengths should be stretched out and redshifted along with what happens to light. What makes gravitational waves an especially intriguing tool for studying the early universe is that in the early universe, the universe would have been at such a high temperature and such a high density, it would have been like a white hot plasma throughout the entire universe. So light couldn't really move freely through the universe until the formation of the cosmic microwave background around 380,000 years after the Big Bang. Because again, the universe just didn't let light through it. The universe was opaque to light. But gravitational waves can pass through pretty much anything. So if we can find a way of detecting them, we could potentially see gravitational waves all the way back to, again, a fraction of a second after the Big Bang. So, but yes, as a shorter answer, gravitational waves do get redshifted. Another question, is it just LIGO taking part in measuring gravitational waves at this moment? So for the method that LIGO uses, basically LIGO, let's see if I can pull up a quick picture of how the LIGO detector works. Okay. So the LIGO detector measures gravitational waves a different way. It takes a laser beam, splits that laser beam into two, and sends it in two different directions. It reflects off some mirrors and then comes back to the source. And when that light is recombined, you can very, very accurately measure any relative length changes in the arms of those detectors. So if a gravitational wave is coming towards a detector and it stretches and squishes those arms of the detector, well, we might be able to measure that effect using this kind of a device. Again, the problem is these effects are very, very small, so you have to get rid of every single other bit of noise. I think I have some pictures of the... did I not include pictures of the detectors? Let me quickly... Let me do a quick Google image search just so I can give them some credit for this. So this is the LIGO detector. I think that's the one in Livingston, Louisiana. So again, these are the arms of the detector, and this is where the laser is generated. And this is one of the most advanced machines in the world. They have the most stable, high-powered lasers ever produced. Those tubes that you're seeing are at the most perfect vacuums ever produced. The mirrors at the end of these detectors to reflect the light back and forth along the detector, they're the most perfect mirrors ever produced. The seismic isolation is phenomenal because they need to reach a sensitivity where those detector arms are about 4 kilometers long each, so around 2.5 miles each. And they're trying to measure length changes 1/1000th the diameter of a proton. That is exceedingly sensitive for what they need to be able to do. There are other detectors like it. There's the Virgo detector in Italy. I don't know if it's online yet, but the CAGRA, I think is the acronym. There's a Japanese interferometer that's going online. I think there's a detector another LIGO detector being developed in India. And we actually want detectors all around the Earth, because if you get multiple detectors around the Earth, you can determine if a gravitational wave signal comes by, you can much more accurately determine where that signal is coming from. So it's a lot easier to look in different directions on the sky for that telescope. So yeah, in this part of the spectrum, there's LIGO, there's Virgo, there's CAGRA. Pulsar timing, that's looking at longer wavelength, lower frequency gravitational waves. For the very lowest frequency, we're looking at patterns in the cosmic microwave background. That one's still kind of ironing out some kinks, and hopefully eventually we'll get Lisa to fill in some of these gaps in our gravitational wave spectrum. So again, lots of different people working doing a lot of hard work in figuring out how to actually make these exceedingly precise measurements, and how to analyze the data and use this as not only a tool of studying the properties of gravity, but of basically allowing this to be a new kind of telescope to study different kinds of physical systems. Were there any other kind of questions out there for now? Well, if there are more... Oh yeah, there's like a 15-second delay, so I should probably wait a little bit more, but if any other questions are being written down, I'll quickly address those, but in the chat, if anyone's like watching this later and has more questions, let me know in the chat, and I'll give it just a few more minutes just to see if anyone has more questions. But if not, enjoy the rest of your day. Again, with the delay, I'm just waiting to see if there's any last questions that come up. This is my first time doing a live stream, so I don't entirely know the etiquette for this part. Okay, well, not seeing any other questions, so again, have a wonderful rest of your day, and if there are questions later on, then throw them into the comments, and I'll try to respond to those. So have a great rest of your day.